Welcome, ladies and gentlemen. Let's go ahead and translate the given matrix equation into its corresponding system of equations. So recall our coefficient matrix A, when multiplied by a variable matrix X, is equal to my constant matrix B. We can go ahead and rewrite that as matrix A, right? Matrix A times my variable matrix X, I'll go ahead and do in green, is equal to this constant matrix. We'll call it matrix B, right? If I rewrite that matrix equation as a system of equations, I know that the coefficients for X, Y, and Z come from the columns 1, 2, and 3 in order. So I can translate this into the original system from which it came simply by grabbing my coefficients on each of the variables X, Y, and Z in order. So that would be 1x minus 2y plus 3z equals, and it looks like 11 was my first one. So I can go ahead and do that each in turn. And so go ahead and tell me the second equation then when I call on you. So let's go ahead and translate. What would my second equation be? Get ready. And Will?
4x minus 1z equals 2.
Nice job handling that zero coefficient on the y term. Did you see what Will did? He knows that a zero coefficient means that there won't be any y in that equation. Nice job. Minus 1 equals 4. We need that for the second one. And then what would I have for my final equation, Aaron?
2x minus 1y plus 3z equals 10.
Awesome. Thank you for your help, you guys. Everybody take a look at our three equation, three variable system, and raise your hand if you translated that correctly. So everybody have that translated? Good job. Now I'm off to solve my variable, my matrix equation. I'm going to solve it for my variable matrix X. And I know that X will be given by A inverse, that is the inverse of matrix A, my coefficient matrix. In order to calculate that, right, I'll use my calculator, but I must have a square matrix in order to be able to calculate its inverse matrix, and so that has to be a square matrix, and then times matrix B, and so that's what we're working towards on our home screen. This is what we're going to enter in order to get my variable matrix X alone. So let's go ahead and in my matrix editor, we'll go ahead and edit matrix A, and I want that to be a 3 by 3, and I want it to be 1, negative 2, 3. And I want it to be 4, 0, 1. Nope, 4, 0, negative 1. And I want it to be 2, negative 1, 3. Take a minute to make sure that I haven't messed up any signs. And then I also need to edit my variable matrix B. And so I'm going to edit, and this time I'm going to edit B. And matrix B I want to be 3 by 1, and it's going to be 11. For, oh, Jiminy Cricket, 10, 11, 4, 10, and finally, the big payoff, we get to go to our home screen, so I'll second quit out. I'm going to call it the matrix named A, so second matrix named A, and then calculate its inverse by pressing that little negative 1 button, A inverse, and then times, I need matrix named B, so matrix named B, and voila! It looks like I get 1.4, negative 2.4, and 1.6. And now I'm going to go ahead and change that into its fractions without having to do each entry individually. Check this out. I'm going to do, right now, I'm going to do math, frac, enter, enter, and it took that original matrix, the variable matrix XYZ that I had gotten alone, and it changed each entry simultaneously into the corresponding fraction. So I got my exact values as fractions there, right? Just by doing math frac, and it changed that matrix into pretty print. So that's pretty awesome. So I like that. I like that even better than my decimal answers there. I mean, decimals taste good. Don't get me wrong, but fractions taste even better. Yum, 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 yum. So it looks like my final answer would be the ordered triple x comma y comma z given by 7/5, negative 12/5, 8/5. Go ahead and raise your hand if you did the matrix equation correctly on your calculator. Is everybody good with your matrix editor? Way to go! And I saw that on your quiz. You guys did a very good job with our chicken and our sodas question with our 3x3 equation matrix. Way to go! All right. At this time, we're going to go ahead and pause the recording while you make sure you have the proper heading for assignment number 5, and we'll check that together. Okay, ladies and gentlemen, today you can see we're going to graph inequalities and systems of linear inequalities in 2 dimensions, on the xy coordinate plane. Your homework was graphing one variable linear inequalities where you did the number line, the boundary numbers, either circled, filled in, right, for closed circles, or left open circles and then shaded in between, or shaded to the right, or shaded to the left, and so on. Today we're going to go ahead and add a second dimension, so we're going to be graphing linear inequalities on the xy coordinate plane. We'll also practice defining the feasible versus non-feasible region, that is the solution region, right? The solution region for our linear inequalities when we have a system. And then we'll use systems of inequalities to model real-world scenarios as we set up for kind of our capstone activity in Unit 7 is called linear programming, where we use systems of linear inequalities to answer real-life questions, to find optimal solutions to problems. And so that's going to be a focus for the second half of Unit 7 after your quiz. All right, let's go ahead and get started with our discussion then. In your note sheet for day 6, today we're graphing inequalities in the coordinate plane, and I want you to go ahead and think about the graph of your homework when you had problems like x is less than or equal to 2. If you're going to graph that on a number line, we need to clarify the boundary number, right? And we need to determine the direction of the shading. And so you should be describing 2 things: your initial point, do I include it or not include it? And then the direction of the ray, do I shade to the right or to the left? Go ahead and tell the class when I call on you. How would I make this graph? X is less than or equal to 2, like from your homework. What would I do procedurally? Ian?
You like put a filled dot on the line and label it to shades to left.
Awesome. Notice how Ian has said this is a closed circle because we do include that as part of our solution set, and then we shade everywhere to the left because there's infinite number of solutions, x, to the satisfies this linear inequality, all of them to the left of or equal to 2. All right, so go ahead and pick out your solution x value based on Ian's graph. Right, what's one solution x value? Nathan? 1. Yes, 1. A different one. Emily?
-2.
-2. Good. A different one. Kenzie?
-8.
-8. Good. What about x equals 2? Yes, because it's inclusive. It's a closed circle. It's included in my solution set. Nice job. Now we're going to up the ante. Yes, that's right. Now what if we were going to include 2 dimensions? That is x and y in my solution set. What? I could still graph the solution set. Instead of being an infinite number of x values, it would now be an infinite number of points, x comma y, just like we've been finding points we've been finding points as solutions to a linear system. Now we're going to have points that are a solution to a linear inequality. So consider the graph. We also need to determine whether or not we're going to include or exclude the boundary, not point, but now boundary line. If we're going to shade to the right or to the left of this boundary line, and so on and so forth. And so, in general, if I'm graphing this linear inequality, x is less than or equal to 2 now in 2 variables, I'm making a picture on a xy coordinate plane with my set of axes. I know that any point whose x-coordinate is less than or equal to 2 is going to satisfy that linear inequality. So I go to my boundary line. It looks like x equals 1, 2. Do I include it? Yes, because it was or equal to, so I'll make that solid. And now I'll go ahead and highlight or shade everywhere to the left. And so I'm going to go ahead and use the highlighter tool because that's pretty sweet, and we'll shade everywhere to the left of that, including the boundary line. That's pretty awesome. Very nice. Everybody pick out your favorite solution point, x comma y, and share with the class when I call on you. So what's one solution point to this linear inequality in 2 variables? Jacques?
2, 0.
2, 0 is on the boundary line, so it is included as a solution point. Good. What's a different solution point? Joe?
0,
0, 0 is another solution point, right? Give me a different one. Andrew.
-3, 7.
-3, 7 is a solution point. Notice how all of these are to the left of my boundary line, x equals 2, right? Every one of those is to the left of or on that boundary line. So I extend my notion of shading or not shading, right? My boundary line, that's going to be solid versus dashed. And do I shade to the left or to the right or above or below? That's going to be my shading up or down the number line, right? Corresponding now in 2 dimensions. Today we're going to refer to my solution points as the feasible region. And so we're going to go ahead and have now a feasible region. Those are all my answer points. Instead of just an array pointing to the x or y values, now we're going to have a whole region pointing to points. Awesome. So that's pretty sweet. So what we're going to do is go ahead and practice a little bit together and make sure we're comfortable, and then you'll get a little bit of work time today. So when graphing inequalities on a coordinate plane, we need to clarify the boundary line. Are we going to include points on the boundary line? If so, we'll make it a solid. We'll make it a solid boundary line. Are we going to exclude those points, right? If it's a strictly inequality, then we'll use a dashed line. That'll show that it's dashed or dotted, that points on the boundary line are not included as part of the feasible region. They're not part of the solution set. We're going to pick the half plane, which includes the solutions. This is the side of the line that we're going to shade. We'll call this the feasible region. If our domain is discrete, the real numbers are lattice points if the solutions are discrete points. And so we're going to go ahead and shade, or we're just going to plot, right, the solution points if we're dealing with lattice points. And we'll take a look at an example with a I Am Sweet Bakery cookie example. I really love cookies. Cookies are so good. And so we'll take a look at that a little bit later. All right, let's go ahead and do one together. Consider the linear inequality 3x minus 4y is greater than or equal to -8. We can handle this a couple different ways. One way would be to make a sketch by using x and y intercepts, since we're already in standard form. So recall, we could make a quick sketch by getting the intercepts of this equation. Since it's in standard form, we could get the x-intercept, and we could get the y-intercept. Connect those two, and that will be my boundary line. So let's go ahead and get the x-intercept by plugging 0 in for y. If I plug in 0 for y and solve for x, I get x equals -8/3, comma 0 would be the x-intercept. So I'll go ahead and write that. -8/3, comma 0. If I plugged in 0 for x and solved for y, I would get y equals positive. I would get y equals +2. So the y-intercept would be 0, comma 2. Let's go ahead and plot those on my xy coordinate plane. So I had -8/3, comma 0. That's -1, 2, and 2/3 is right about here. And we had 0, comma 2 as my y-intercept. Next, we'll go ahead and connect those with either a solid or a dashed line. We need to go ahead and consult the inequality just like you did for your homework assignment. If this is a greater than or equal to, right, are points on my boundary line included or excluded from my solution set? Mark?
Included.
Included. So I'll show that by having a solid line. A solid line. So when I draw my line, I'm going to go ahead and make sure that it's a solid line. So I'm going to go ahead and do a solid line that connects these points. And it would be pretty sweet if we made this arrow, arrow, and solid, and maybe red. Very nice. Now that we've got our boundary line clarified, that is, solid includes points on the boundary line. That's as part of the solution set. Dash would be excluding for strictly. Now we're going to go ahead and pick the half plane, which includes solution. So we can do that, determine that by picking a test point on either side. I like to pick a test point that's easy to evaluate in the original inequality to see if it makes a true statement. If the solution point, the test point makes a true statement, then all the points on that side of the boundary line will also make true statements, and that's the side I'll shade. If the test point does not satisfy the linear inequality, then all the points on the same side are not going to satisfy either, so I'll shade the other side. Let's go ahead and pick 0, 0, because that's an easy one to evaluate. So for my test point, I'm going to go ahead and pick 0, 0, and see if that satisfies linear equality. Let's try. If I plug in 0, 0 into my original inequality, 3 times 0 is 0, minus 4 times 0 is 0. Is 0 greater than or equal to negative 8? 0 is greater than negative 8 because it's a greater value than negative 8. And so yes, 0, 0 does satisfy the inequality, which means that everything on this side is going to satisfy it as well. So I'll go ahead and shade in that side that includes my feasible point. That includes my test point. So all of the values on this side of the boundary line are going to be included. I will label this the feasible region. All the points in the feasible region are potential solution points. Everybody go ahead and pick your solution point. So what's your solution point from the feasible region aside from 0, 0? Caitlin?
2, 0.
2, 0 is in the feasible region. Good. Give me a different one. Taylor? 5, 1 is in the feasible region. Good. Give me a different one. Emily?
4, 2.
4, 2. Good. All those are our solution points. What about 2, 0? Oh, there I got it. What about 0, 2? Yes. Because it was a solid line, it will be included, all those points on the line below. Okay. The second way to do this problem would be to solve for y in graph using slope-intercept form. And so we could rearrange that. If we wanted to do this a different way, we could rearrange this by subtracting over the x term, dividing everything by negative 4, and when we divide by a negative, we need to change the direction of my inequality statement. So when we divide by a negative 4, this greater than or equal to now becomes a less than or equal to. Negative 3 divided by negative 4 is positive 3/4 times x, and then negative 8 divided by negative 4 is plus 2. Notice how a graph of this boundary line should mirror my original standard form sketch using intercepts. That is, plot the y-intercept. The y-intercept would be 2, and then count out my slope number up 3. 1, 2, 3, and over 4. Count down 1, 2, 3, and over 1, 2, 3, 4. Notice how if I graphed it this way, I'd still get the same boundary line. However, my shading now, I could do by looking at my symbol. I want all the solution points whose y-coordinate is less than or equal to my boundary line 3/4 x plus 2. Visually, do you think these points would be above or below for a y less than equation? Well, y less than or equal to would be all the points whose y-coordinates is less than, is below that boundary line. And so if you solve for y, then you can just look at the symbol and say, less than I shade below, greater than I shade above. You see? So that's two different ways you can do the same problem. Awesome. Let's go ahead and do some practice problems together. So if you find your 5, 7, 5, 8 practice, we're going to go ahead and do a couple of these together. Firstly, let's graph the inequality 3x plus 5y is less than or equal to 15. Would you rather graph this by using x and y intercepts or by solving for y? Would you rather make a quick sketch with x and y intercepts or by solving for y? The choice is yours. Which would you rather do? Cody? Solve for y. We could do that by subtracting over the 3x. It's 3x, and we get 5y is less than or equal to negative 3x plus 15, and finish it out by division. Just make sure that you're being careful with the linear inequality. If I divide both sides by 5, do I need to change the direction of my symbol? No, only when I multiply or divide both sides by a negative. So this remains y is less than or equal to negative 3/5 x plus 3. Everybody pick out the y-intercept of this line and tell the class when I call on you. Y is less than or equal to negative 3/5 x plus 3. What would my y-intercept be here? Rachel? 0, 3. Good, thank you. So 0, 3 would be my y-intercept. Go ahead and tell the class the slope of this line when I call on you. What would my slope be? Jacob?
Negative 3 over 5.
Good. And so my slope is negative 3/5. So I count from this point down 1, 2, 3, and over 5. 1, 2, 3, 4, 5. I can even go backwards. 1, 2, 3, and then 1, 2, 3, 4, 5. Next, will my boundary line be solid or dashed? Will my boundary line be solid or dashed? Chrissy?
Solid.
Solid, thank you. Because I'm on a greater than or equal to or less than or equal to, I'm going to include the boundary line, so I'll make it solid. And I'll do some arrows. And solid and blue. Very nice. And now I decide about shading. Because Cody chose to solve for y, I can pick my shading based on the inequality symbol itself. If this is a less than or equal to, am I going to shade above or below the boundary line? Maya?
Below.
Below. If it's a less than or equal to, I'll shade below for my y coordinate to be beneath the boundary line because we solved for y. If I didn't solve for y, I choose a test point, like 0, 0, and see if it satisfies the inequality. 0 plus 0 is 0. Is 0 less than 15? Less than or equal to 15? Yes, so I shade below the boundary line in either case. Let's check the answer. Survey says you are correct. So we have a boundary line, it's solid, and we shade below. Just in case you weren't awake on a Monday, here's some lime green to wake you up. Ta-da! Zing! And we label the feasible region. So we label that feasible. Awesome. Okay, let's go ahead and go backwards. Let's see if we can generate a linear inequality based on its picture. So, if I know the feasible region is the top right of this, the top right half plane on this graph, I could go ahead and write a linear inequality to depict that feasible region based on my knowledge of the boundary line. So let's go ahead and pick out the y-intercept of that boundary line. It looks to me like the y-intercept of that boundary line, right, would be what, Hannah? Negative 2, and so if my y-intercept of the boundary line was negative 2, and then I can count out the slope by doing rise over run, so it looks like everybody get the slope. So what does the slope of that line appear to be? And what does the slope of that line appear to be, Joe? Negative 1. Thank you. If this were an equation, my boundary line would have equation y equals negative 1x minus 2. But it's not an equation. It's an inequality. So we now need to decide what symbol would go here. Well, is my boundary line, is my feasible region above or below the boundary line? Carson? Above. So should I have a greater than or a less than inequality symbol? Caroline?
Greater than.
Greater than. Good. Is my boundary line solid or dashed? Caitlin? Dashed. So should I have a strictly or equal to? Strictly or equal to? Jacob?
Strictly.
Strictly is right. So I've got a greater than because my feasible region was above my boundary line, and I've got a strictly because it's a dashed line. Go ahead and pick out a solution point to this inequality shown. Share with the class when I call on you. What's a solution point to this inequality shown? Hans?
5, 5.
5, 5 is a solution point. A different one. Megan? L?
4, 4.
4, 4 is a solution point. Good. What about negative 2, 0? No. How come, Jacques?
Because it's a dashed line, which means it doesn't include stuff on the line.
Absolutely. My feasible region does not include boundary line points because it's dashed. It's a strictly. Good job. Hey, did we get that? Yeah, we did. Yeah, we did. Yeah, you did. Yeah, we did. All right. Let's consider a bakery problem because it's always a good time to eat cookies. In fact, I'm hungry all the time. I don't think it matters where lunch is or if I just ate or not. I'm always hungry, and I'm especially always hungry for cookies. So I Am Sweet Bakery sells chocolate chip cookies and plain oatmeal cookies for $1.75 a dozen. Connie has $7 to spend on cookies. At the right, we could graph possible combinations of chocolate chip cookies and plain oatmeal cookies she can afford. If each dozen cookies costs $1.75, let's see how many cookies she can, or how many dozens she can buy. So how could we determine how many we can buy? So she's got $7 to spend, and I want to see how many times $1.75 goes into that. So it looks like 4 dozen is the most you could purchase, right? It looks like 4 dozen is the most you could purchase. And this way we can determine my feasible points. If we can't buy a portion of a dozen and are restricted to buy whole dozens, she could buy up to 1, 2, 3, 4 dozen plain oatmeal, or up to 1, 2, 3, 4 dozen chocolate chip, or a combination that totals to 4, like 3 and 1 or 1 and 2, anything less than 4 dozen total, right, would allow her, she'd be able to purchase without going over $7. Is that the way you guys are interpreting this? All right. So go ahead and determine with your partner if she can buy 3 dozen plain and 3 dozen chocolate chip. Let's do a Y or an N for yes or no. A Y or an N, and a Y or an N, and then we're ready to share. Okay, so yes or no for each of these in order. What did you guys get for yours? Blake and Mitch?
No.
No?
Yes.
Yes? No? Yes, no. No, yes, no. Raise your hand if you had no, yes, no. Hooray! No, yes, no for A, B, and C. Okay, no, yes, no. Yes, no, no. Yes, yes, no. Go ahead and decide. The feasible is beneath. Right, see that? The feasible is beneath. Good. Okay, ABC, yes, no, yes or no in order. 1, 2, 3, ABC. Caroline and Kinsey?
Yes, no, and no.
Yes, no, no. Survey says. You have absolute power. Yes. Very nice. Who had yes, no, no in that order? Yes, no, no. Good job. We're killing it. All right, let's go ahead and graph the following systems of inequalities. And I want you to go ahead and take a look at these first 2 boundary lines. X is greater than or equal to -2. And y is greater than or equal to -3. These are my specials. Remember we saw from our warm-up question that x is greater than or equal to -2 is a vertical boundary line. And so my y greater than or equal to -3 must be a horizontal boundary line. So let's go ahead and take a minute to sketch those. as you continue entering your boundary lines, I want you to think about the feasible region. Remember, the solution to a system of linear inequalities must be the overlap of each linear inequality's feasible region. So we have to find those solution points to satisfy every single inequality. Just like when we solved the system, our solution point had to satisfy each equation in the system, so too must our solution points, our feasible region, satisfy each inequality in a system of linear inequalities. So let's go ahead and see if we can put it all together. We want to the right or to the left of the red boundary line for x greater than or equal to -2. We want to the right or to the left of that for x greater than or equal to -2. Chrissy?
What's the question?
Do we want to shade to the right or to the left of that red boundary line, given that my inequality is x is greater than -2?
It would be to the right.
To the right, absolutely. So x greater than means shade to the right of. Good. If we want to shade above or below this blue boundary line, y is greater than or equal to -3. So y greater than or equal to -3, do you think we should shade above or below the blue? Above or below the blue? Jacques?
Above.
Above, because it's y greater than, we're going to shade above. Good job. So we want to the right, we want above, and now let's go to my slant lines. So green slant line, here we go. Y less than -x plus 1. Do I want to shade above or below than my green boundary line? Kendall?
Below.
Below, good. And so you guys are picturing this? We're right, we're above, we're below, and lastly the black line, y greater than or equal to positive 1/3, x minus 3. Notice how I flip the direction, you guys. Why did I change the direction from this black inequality to this red inequality? Right? Why did we change that direction? What happened there? Mark?
Because we divided by negative.
Good. We divided by a -3, and when we do that, we need to change the direction of my inequality because I'm multiplying by a negative number. Good. So this is y greater than. Everybody look at the black line. Above or below the black line then? Joe?
Above.
Can we do it? Can we do it all? I think we can do it all. Let's do a green highlighter. That would be pretty sweet. So we want... Huh? How do we do? Yeah? Pretty sweet color. All right. We ready to take the answers? We ready to check? You ready to check? Bam! FR. FR, what does that bar stand for?
Feasible region.
Feasible region. Thanks you for keeping it school appropriate. I appreciate that, Emily. I appreciate that. All right. Go ahead and write a system for the linear inequalities, and we're going to go ahead and do top left half plane, the top left half plane there. Be ready to share your response with the class. Okay, what's one boundary line? What's one boundary line inequality? Cody?
Y is greater than or equal to -2 plus 4.
-2 plus 4/3 x. Let me see. You must be talking about this 1 because negative 2 is the y-intercept, and up 1, 2, 3, 4, and over 1, 2, 3. Nice job. And why did you pick or equal to, Cody? Oh, I'm sorry, just go or equal to solid, and then shade above for the greater than equal to. Absolutely, good job. Thank you. What did you get for the other boundary equation? The other boundary equation, Hannah? Negative 1/3 x minus 4. Let me see, minus 4, and then be down 1 over 3, so back 3. Awesome work. Raise your hand if you got each of these. Above solid, above solid. Good job, you guys. Awesome. Pretty print survey says you are correct. Good job. Did I do minus? I did. Good job. Okay, so let's go ahead and close it up with a real world application to set us up for linear programming, which we'll be investigating and introducing on Wednesday's class period before spring break. So let's go ahead and take a look at this problem. A sack of NutriPlus parakeet seed contains 8 pounds of white millet and 2 pounds of red millet. A sack of UltraGrow parakeet seed contains 6 pounds of white millet and 4 pounds of red millet. Seed and Feed currently has 9,000 pounds of white millet and 4,000 pounds of red millet in stock. So I want you to consider the number of sacks that NutriPlus N and UltraGrow sacks U that Seed and Feed could package. And so they take this bulk, right, this bulk red millet and bulk white millet, and they make NutriPlus sacks to sell, and they make UltraGrow sacks to sell their parakeet seed. What we want to do is translate the given information into a system of linear inequalities. So I'm going to go ahead and we're going to talk about this together to set up our activities on Wednesday. So let's go ahead and make sure that our N, number of sacks of NutriPlus, and U, number of sacks of UltraGrow, are non-negative. So we're going to go ahead and get 2 inequalities for free. Make sure that we have N greater than or equal to 0 and U greater than or equal to 0 because we can't have a negative number of sacks, right? So we go ahead and have those 2 for free. Next, let's go ahead and consider the white millet contribution. For every sack of NutriPlus that we package, that uses 8 pounds of white. And so that's where this 8 multiplier comes from in our linear combination. Kind of like our student ticket contribution to sales versus adult ticket contribution to sales. Well, every NutriPlus pack takes 8 pounds of white millet. Now go ahead and find the UltraGrow contribution. So it looks like 6 pounds of white millet for every UltraGrow U sack we package. That's where that 6 came from. How much white millet do we have on hand? 9,000 pounds. So we can do at most, right? At most 9,000 pounds for the white millet equation, or inequality rather. That's why we get less than or equal to. Now let's go and do the red millet equation. My red millet, 2 pounds for every NutriPlus. That's where this comes from. That's where my 2N comes from, right? Because every NutriPlus sack takes up 2 pounds of red millet. And then 4 pounds of red millet from every UltraGrow. That's where this came from. And how much red millet do we have on hand? 4,000. So we could package at most, right? At most 4,000 pounds. That's why it's less than or equal to. Great. Now let's go ahead and make our picture. And so we can get X and Y intercepts, in this case N and U intercepts respectively, in order to make my picture. Everybody, let's go ahead and do this first equation. Let's do this first equation and we'll get our N intercept. What? Well, we can get an N intercept just like we get an X intercept by plugging in 0 for Y and solving for X. Well, we're going to plug in 0 for U and solve for N. Everybody, let's do that now. So if I plugged in 0 for U and solve for N, I'd get N equals 9,000 divided by 8. So let's do 9,000 divided by 8. it looks like 1125 is my n-intercept from the first equation. So 1125, comma 0. That's how we got this point right here. Right? That's how we got that 1125, comma 0. We could get the u-intercept in the same way. My u-intercept would be given as the value of u when n equals 0. So if we reverse that and plug in 0 for n, we'd get 9,000 divided by 6. Everybody do it. And that's where we get the 1,500. The 1,500 value of u when n equals 0. So that's right here. All right. We can do the same thing for that second equation. All right. The n-intercept in the second equation when u equals 0, n equals 4,000 divided by 2 is 2,000. That's how we get this point. When n equals 0, u equals 4,000 divided by 4 is 1,000. That's how we get this point. All right, you guys, if we were to solve these for u, right, by subtracting and dividing, notice how each of these inequalities would be less than for the slant lines. So less than would shade above or below. Well, less than would shade below. Less than would shade below. Greater than 0 would shade to the right. Greater than 0 would shade above. And that's how we get this feasible region. Okay? So this is going to be a setup for our linear programming activities starting on Wednesday, where we have a system of linear inequalities in the contextual situation complete with units, and we get a feasible region, and then we'll use that feasible region to find an optimal solution. That's pretty sweet. What questions do you have about our parakeet seed? I wonder if you give the ultra go, you know what I mean? Does that like bulk up your parakeet? You know what I mean? Like creatine parakeet? Let's go ahead and sum it up. So given the boundary line, y is greater than negative 3/4 x plus 2, please respond to the following questions. Don't say it out loud. Instead, I want you to go ahead and get a written response for each. I'll pause the recording and we'll come back to share our responses. Okay, ladies and gentlemen, let's take a look at our closure for the day. Given this linear inequality, y is greater than negative 3/4 x plus 2, is the boundary line solid or dashed? Solid or dashed? Emily?
Dash.
Dashed? Raise your hand if you have dashed. Dashed? And why would that be dashed, Chloe?
Because it's just greater than, it's not equal to.
Absolutely. It was strictly greater than, not greater than, or equal to. Nice job. Is the feasible region above or below that boundary slant line? Is it above or below? Mark?
Above.
Above? Why did you say above?
Okay, it's greater than.
Good. Raise your hand if you also had above. Who had above for that? Good. Number 3, is 0, 1 a solution point? Why or why not? So 0, 1 a solution point? Why or why not? Andrew?
No, because when you plug it into the log equation, the answer is not. The answer is not less than 1.
Good.
Why?
1 is 1 greater than 2? No, 1 is not greater than 2. So 1 is not greater than 2. That does not satisfy the original. Good. Take a look at the last one. Is the point 4, negative 1 a solution? Why or why not? Caroline?
No, because if you plug them in, it would be 1 is greater than, or negative 1 is greater than negative 1, which isn't true.
Oh, good. So this time we were on the boundary line. Negative 1, right, is not greater than negative 1. It's equal to, and because this was a strictly, means that it's not included. Nice job, you guys. What questions do you have about your inequality practice? Then you guys are going to have a little bit of a chance to work on now assignment number 6. Nice chunk of time. I'll go ahead and stop the recording and upload it to our Moodle site, as well as export the note.